Hey everyone, let's talk about this idea of an ABCD matrix in microwave engineering, or what its more technical title is a transmission matrix. Now, up till now, we've already addressed this notion of an impedance matrix, Z. We have the admittance matrix, Y. And then we did the scattering matrix, S. And we found that these are all just different ways to talk about and characterize a given circuit or complex device in terms of just these measurable little parameters, right? So what makes the ABCD matrix interesting is that it just represents a specific kind of common case of the 2x2 network. Now, again, we talked about this notion of an n-port network, right? So you imagine something like a black box, and there could be a transmission line here and a transmission line here and here and here and here. So there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 17 n ports on this particular black box. But in practice, it's generally pretty rare to have a 17 by 17 kind of system, right, or a 17 port network. In reality, it's far more common, or in practice, it's far more common to specifically work with a 2x2 network. And usually it will look something like the following, where you'll have some voltage here, so we'll say V1, and then there'll be some current kind of going in there, I1. And then there'll be some other port over here, which we'll call V2, and there will be some current coming out of it, I2. So this is a 2x2 microwave network. And the reason why 2x2s are interesting is because oftentimes complex microwave circuits don't come in the form of these n by n's, but rather a cascade of these particular black boxes, right? So what you would have really a far more practical common system would be, if you want to speak of n sort of port microwave networks, you would really be seeing something that kind of looks like the following, where one is feeding into the other like this. Okay, and we'll just kind of keep going. So this is called a cascade, right? So I have some input here, and something happens within this box, which then feeds to the next box, which feeds to the next box, and so on and so on. So to give you sort of like a real world example, you can imagine something that might look like the following. Here's an antenna, and then it will feed into a transmission line of some particular length, like so. So you have this device here collecting energy from far away, and then there'll be a length of cable, which will probably feed into something like an amplifier here. So there'll be maybe a gain there, a low noise amplifier. And then, this will probably feed into something like a bandpass filter, say, like that. Okay, and then this might feed into a mixer, which might then feed into another bandpass filter, which might then finally feed into yet another amplifier, before finally going to something like an analog to digital converter, or perhaps a speaker or whatever, that kind of thing. So you see, this notion of a cascade is actually what a real world device will very commonly look like. So this idea of the transmission matrix as a cascade of 1, 2, ... all the way out to n little ports or black boxes with an input and an output is a far more powerful concept in terms of creating a complex system, because you have this idea of a signal getting processed in these individual little steps, right? So we receive, we amplify, we filter, we mix, we filter again, and then we amplify again, and then we sample, say. So think of complex systems in terms of it's more useful to think of these complex systems not as an n by n network, but rather one thing feeding into the next. So that is going to motivate our definition for the ABCD matrix. Okay, so let's go ahead and define the basic parameters for a transmission matrix, or as it's commonly referred to as the ABCD matrix. So you just imagine a simple black box, like so, and it's going to have an input port and an output port as follows. So I'm going to say plus minus, there's a V1, then there's a plus minus over here with a V2. There's going to be a current here, I1, and then a current over here, I2. So what I'm going to do is simply define a relationship between the input and output as follows, like this. So V1, I1 is going to be a vector here. That is going to equal, I'm going to write A, B, C, D. And then I'm going to write V2, I2 over here. So you see this matrix here simply captures the connection between the input and the output over here. Or you can also think of it as a system of linear equations, where I would say V1 is equal to A V2 plus B I2, and then V2 is equal to C V2 plus D I2. So why is it useful to define the ABCD matrix over here? Well, the reason is because we want to eventually think about the world in terms of a cascade, right? So we're rarely just going to have a single input with an output. Usually this guy is going to continue on to feed yet another system like so, which may then again feed yet another system like so, and so on. So we'll imagine yet another system over here. I'm going to say plus or minus, this will be V3, and there will be an I3 over here. Now, a quick note on conventions. And traditionally, we've kind of thought of the current as maybe flowing into the device at different ports. But for the sake of the ABCD matrix, the current is flowing to the right. So technically, you have to imagine there's a minus sign on this current here relative to other conventions we've defined. That is to say, when we did an impedance matrix, we implicitly defined a positive current as going in. In the context of an ABCD matrix, a positive current is going to the right. So that's a little trick in convention that we have to be mindful of moving forward. So if I have now this guy feeding into this guy, and again feeding into this guy, what happens is we can write another ABCD matrix for this relationship here, right? So I would, instead of just saying ABCD, for the first one, I'll say A1, B1, C1, and D1, like so, representing, this first box here, box number 1. So this will be number 2 over here. So I'm going to write V2, I2 is equal to A2, B2, C2, D2 times V3, I3, like so. So for simplicity, let's just call this matrix here, I don't know, M2 right here, and this one here was M1, like that. So what I'm going to do is basically just substitute this over to here, and you'll notice something interesting happens. I get V1, I1 is equal to M1 times V2, I2. So that's the ABCD matrix there. But this is this little block here, so that becomes M1, M2, like so, times the vector V3, I3, like so. And you can see I can repeat this all the way out to n different inputs and outputs, right? So if I add a third and a fourth and a fifth and all the way out to n, you just get this multiplication of these matrices, right? So I can more generally write something like this, where I would say V1 is just going to be M1, matrix 1, for this little ABCD network here. And then that feeds into the next, which will be M2, which feeds into the next, M3, dot, 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 M sub n. So there's n of these boxes here. And then the output will just be V sub n plus 1, I sub n plus 1. So that's a very handy property, because it just tells us that a large cascade of all these inputs and outputs, if I want to relate to the output to the input, I just multiply all of these little individual linear systems together using matrix multiplication. So that is a nice, powerful, handy property for describing very large, complicated things as just a very simple linear operation.